pursuit of the perfect conductor has long been the holy grail of condensed matter physics. But with the emergence of topological insulators, we have finally arrived at a material class that fundamentally rewrites the rules of electrical transport. To understand why these materials are being hailed as Graphene 2.0, we must first confront the massive, inherent inefficiency of every electronic device currently in existence. Every time you power on a smartphone, a laptop, or a server rack, you're witnessing a thermodynamic failure. These devices get warm because of electrical resistance, a process where electrons, as they drift through a standard copper or silicon wire, are constantly colliding with impurities, structural defects, and vibrating atoms within the lattice. Every collision is a funeral pyre for energy. The kinetic energy of the electron is converted into heat, slowing the processor and draining the battery. This is known as Joule heating, and it is the hard wall that Moore's law is currently crashing into. Topological insulators provide a radical escape from this thermal bottleneck through a bizarre and beautiful quantum paradox. On a structural level, these materials are schizophrenic. If you look at the interior, the bulk of the crystal, it is a complete insulator. It has a large energy gap that prevents electrons from moving at all. However, the surface of the material tells a completely different story. Due to a mathematical property known as topology, the surface or edges of these materials act as perfect, frictionless conductors. This conduction is not just a surface-level coating, it is a fundamental globally protected state of the material's quantum wave function. This means that the electricity doesn't just flow, it flows with a mathematical robustness that makes it immune to the scattering and defects that ruin standard conductors. To visualize the depth of this shift, imagine a crowded hallway where hundreds of people are trying to run in opposite directions. They're constantly bumping into each other, stumbling and losing their momentum. This is the interior of a standard copper wire. Now imagine a hallway where everyone is forced into strict, separated lanes based on the direction they are spinning. In a topological insulator, electrons exhibit a phenomenon called spin momentum locking. An electron's direction of movement is tied directly to its spin state. If an electron is moving to the right, it must be spinning up. If it is moving to the left, it must be spinning down. Because of this, an electron moving to the right cannot be knocked backward or scattered by an impurity because to do so, it would be forced to flip its spin, which is energetically forbidden by the laws of physics in this state. This is called backscattering suppression, and it is the mechanism that allows for the transport of electricity without the generation of heat. This is why the scientific community refers to these materials as Graphene 2.0. While graphene is famous for its high electron mobility, it is difficult to control because it lacks a band gap. It is hard to turn off. Topological insulators, however, offer the best of both worlds. The exotic high-speed Dirac physics of graphene on the surface with a stable insulating gap in the bulk. This opens the door to a revolutionary field known as spintronics. In traditional electronics, we use the charge of the electron to process information. In spintronics, we use the electron's spin. Because spin-polarized currents in topological insulators move without resistance, we can theoretically build processors that are 1,000 times faster than silicon while consuming only a fraction of the power. We are talking about the end of thermal throttling and the beginning of a new era of lossless, high-performance hardware that can operate at the limits of quantum speed. Beyond just better smartphones, topological insulators are the foundational building blocks for the next generation of quantum computing. When a topological insulator is placed in proximity to a superconductor, it can host exotic particles known as Majorana fermions. These particles are their own antiparticles and are highly stable. They are the key to building topological quantum computers, which would be vastly more resistant to environmental noise and decoherence than the systems currently being tested by tech giants. This isn't just an incremental upgrade, it is a shift in the physical substrate of human civilization. We are moving from a world of leaky electronics where energy is fought for and lost to a world of topologically protected information where the physics of the material itself guarantees the integrity of the signal. Deeply and honestly, we must admit that the engineering challenges ahead are significant. Growing these crystals to a level of purity where the bulk remains perfectly insulating while the surface remains conductive is an immense challenge. But the promise is undeniable. The silicon age was built on our ability to switch current on and off. The topological age will be built on our ability to direct the flow of energy with zero loss. This is the material science equivalent of moving from a dirt road to a vacuum-sealed magnetic rail. It is the infrastructure of a future where compute is no longer limited by how much heat a fan can dissipate, but only by the fundamental laws of the quantum universe. To understand topological insulators is to understand that we are no longer just manipulating matter. We are harnessing the very geometry of reality to build a more efficient world. The electrons are ready to move. We just had to build them the perfect road. This is the Graphene 2.0 revolution. and it doesn't lose a single electron to heat. To dive even deeper into the implications, we must consider the environmental and geopolitical stakes of this material. Our current global infrastructure is struggling under the weight of data center energy consumption. As AI models grow and the demand for real-time computation scales, the energy required to cool these facilities is becoming a significant percentage of total global power usage. Topological insulators offer a way out. By eliminating the heat at the source, the transistor level, we can reduce the carbon footprint of the digital world by an order of magnitude. This is not just a laboratory curiosity, it is a requirement for a sustainable digital future. Geopolitically, the race to master topological insulators is the new space race. The nations and firms that secure the patents and the manufacturing techniques for high-quality bismuth telluride or mercury telluride will dictate the performance limits of every defense system, every medical research supercomputer, and every financial algorithm for the next century. Honesty also requires us to look at the Berry phase and the quantum spin Hall effect that underpin these materials. These are not concepts that appear in everyday life, yet they are the invisible architecture of our reality. The Berry phase is a geometric phase factor that an electron's wave function acquires as it travels around the surface of a topological insulator. This phase shift is what ensures that the electron states are robust. Even if you dent the material or if there is a massive impurity in the way, the electron will simply flow around it without losing its spin orientation. It is a form of quantum immunity. It is as if the electron is not just a particle but a wave that knows the shape of the surface it is on. This global awareness of the material's geometry is what makes it topological. In a world of increasing complexity and entropy, finding a system that provides such absolute mathematically guaranteed stability is nothing short of a miracle of modern science. The transition to topological insulators will not happen overnight. It will require a complete redesign of how we fabricate chips and how we think about logic gates. But the roadmap is clear. We are moving toward dissipationless electronics. This means we will soon have devices that can process more information than the human brain while staying as cool to the touch as a piece of marble. This is the true potential of the Graphene 2.0 era. It is a future where the friction of the physical world no longer hinders the speed of thought. By building these topological highways, we are creating the hardware that can finally keep up with the software of our imagination. The electrons are no longer crashing, they are gliding. And in that glide, we find the future of power, speed, and efficiency. The era of wasted heat is ending. The era of the topological insulator has begun. Ultimately, the goal of this technical roadmap is to prepare for the inevitable shift in physical substrates. We must move beyond the limitations of silicon if we are to achieve the levels of computation required for planetary scale challenges. Topological insulators are not just a component, they are a manifesto. They represent our refusal to accept energy loss as an inevitable part of progress. They are the promise that information can move with the same purity as the vacuum of space. By mastering the topology of the subatomic, we are ensuring that the digital infrastructure of tomorrow is as robust, efficient, and permanent as the mathematical laws that govern it.